Hello everyone, welcome to this new video tutorial. In this video tutorial, we will be combining YOLO11, which is an object detection model, with SAHI, which stands for Slicing Edit Hyper Interface. It's basically a computer vision tool that improves object detection, especially for small or tiny objects, by dividing the image into smaller overlapping patches, and then it runs object detection model on each patch. So let's look at the GitHub repo of Sahi. You are already familiar with YOLO11, which is released by Ultralytics. It's an object detection model. So in this tutorial, we will be combining YOLO11 with Sahi so that we can improve object detection for small or tiny objects. So over here, you can see we have this Sahi GitHub repo over here. So Sahi stands for Slicing Edit Hyper Interface. It's a lightweight computer vision library performing large-scale object detection and instant segmentation. So let's look at this first example over here, which is in front of us. So like imagine if you have a big photo or a video with tiny objects like small bricks or like distant cars over here, as you can see over here in this example as well. So a normal object detection model might miss like detections, like might miss cars over here, might not be able to detect all the cars very correctly, because you can see that here you can see we have cars and they are very small objects. So as they are too small compared to the full image, so a normal object detection model might miss them, might miss to detect them. So in this case, we will use Sahi. So Sahi solves this problem that normal object detection model faces, like normal object detection model might not be able to detect all the objects over here. So in that case, we will combine uh, Sahi with the object detection model. So what does Sahi do is cut the image into smaller parts. Like you can see over here, the Sahi will cut the image into smaller parts. Then it will run the object detection model on each small part. Then in the last part, it will combine all the detections from those slices and it will generate a final output. Okay. So here you can see we have this complete GitHub repo over here. Like you can see installation step are provided. There are many tutorials available over here and like different demo videos and Google Colab notebooks are being available over here. So why you should use Sahi? Like you might be thinking why we should use Sahi, because you should use Sahi with your object detection model, because with the help of Sahi, you can improve small or distance object detection. Like you can detect small objects or objects that are far away better with the help of Sahi. And Sahi also improves model performance on higher resolution images. Plus, it works well with any object detection model like YOLO, RFT, TEDR, or faster on CNN. And so if you're using YOLO model and it might miss small objects in the image or the video, then you can integrate Sahi with your YOLO model to get better results by slicing the image. So this is a quick intro and about the Sahi. So in this tutorial, we will be combining YOLO11 with Sahi. So let's get started. So now I will just go to the PyCharm Community Edition and I will just start writing the code from scratch. So over here, you can see that I have created a project in PyCharm Community Edition. So these are the two libraries that we will be requiring in this tutorial. So Ultralytics and Sahi, because YOLO11 is available under Ultralytics package. To install this library, you can simply write pip install requirements.txt and run this. So now you can see requirements already satisfied because I've already installed these packages. But if you are installing these packages for the first time, this will take some time. So now I will just start writing the counter code. So first of all, we will import all the required libraries over here. So I will just import OpenCV When you install Ultralytics package, OpenCV package also get installed with it. Then we will import time. Then from Sahi, we will import auto detection model. Okay, and then from Sahi dot predict, I will import get slice prediction. Then from Sahi dot utils dot Ultralytics, I will import download model weights, so I can download the Ultralytics YOLO11 model weights directly. Then from Ultralytics utils files, I will import increment path over here. Then from Ultralytics utils utils import select device. So these are the libraries that we will be requiring in this tutorial. Then I will just create a class by the name Sahi Inference. Okay. And what I will do is, so here we will find a detection model over here, none. So first we want to load the model. So we have the input parameters as weights and device. Like if you have the CUDA device, or if you have a CPU. So I don't have a GPU in my local machine, so I will not write CUDA in the device. Instead, I don't have a GPU in my local machine, so I will be writing device as CPU over here. Then I will just define the weights path over here. So here I just want to save the YOLO11 model weight. So instead of this, I will just create a directory over here by the name models, and inside this directory, I want to save the YOLO11 model weights. So I will just write over here models. So first we have the detection model. So we will be using the pre-trained YOLO model, pre-trained YOLO11 model. So model. First we need to define the model type. So YOLO11 is available under Ultralytics package. And in the model path, we have the weights path. Now we'll just create another function by the name run. The input parameters will be source. Then we have the weights as the input parameters. Then we have the device, which will be CPU. We want to view the output image, so we'll just set it by default true. Want to save the output video, so we'll set it true as well. I don't want to show the confidence score, so we can just set height confidence is equal to true. Or if like you might want to show the confidence score, so we can just set it false. Then we will set the slice size is equal to 5. So you might be thinking, what is the slice size? So now you can see that I just like the slice size width as 512 and the height as 512 as well. So a complete image or a frame will be sliced into patches of size 512 cross 512. Each patch will have a width of 512 pixels and the height will be also 512 pixels. So if you have an image or a frame, it will be split into 512 cross 512 overlapping patches. And then we will run YOLO11 object detection model separately on each patch. Then with the help of Sahi, or the Sahi will merge results from all the patches, and it will also take care of the overlapping patches as well. And we want to also save the results in a output video. So I will just write the output video name as output.mp4. So I will just say cap is equal to cv2.video capture. Here I will just pass the input video path. So we add assert to make sure we are able to read the video. Else So then we have a save directory. Okay. So here we'll just define the path where we want to save the output video. So I will just create another directory and name output video. Okay. Increment path, and we will save the output video over here. So if it exists, okay, it's true. And if it doesn't exist, it will just create this directory. So we have already created this directory. So let's write save dash directory. Parents is equal to true. As is okay. That works. Then we also want to save the output video. So we need to define the width and the height. So I will just write int gap.get cv2.gap dash frame width, and we will also define the height. So we'll just write int gap.get cv2.gap dash frame height, and we will also calculate the FPS as well. So the FPS score will row because I'm running it on a CPU machine. So if you just run it on GPU, the FPS score will definitely be high. Okay. Next, we need to define the output video writer over here. So just write video writer is equal to none. If the user select the save image, then we'll only save the output video. Right. Here I will just write video writer is equal to cv2 dot video writer. And we will just save the output video into this directory, which we have find output video. And we have already passed the output video name as output.mp4. Then here we will just define the input FPS, like how many frames we will save in a second. And here we will just pass the width and the height of the output video. Going ahead, we'll load the model. So like you can see, we have the model weights over here. Here we'll just define the weights. Yes, okay. So now we'll loop through the video, each video, complete video frame by frame. So if you are able to read the video, then it's right back frames equal to cap or read. If you are unable to read the video, then this loop will break. Then we have the start time. So we will just be calculating time so that we can calculate the FPS frame per second. The FPS will tell us how many frames are being processed in 1 second. Okay. So now I will just write over here results is equal to get slice prediction. The input will be over here, the frame. Then we have the reduction model over here, which will be self.detection. So our image will be split into, or the image will be sliced into the patches of size 512 in width and 512 in height. So we have already defined this above. Okay. Like you can see over here, slice size. So we have slice size. In the first, we have the width, and the second, we have the height. Now, from here, we will get the our results, like the prediction. So inside this, we will have our bounding box coordinates as well. So inside this results, we will have our bounding box coordinates, class name, confidence score. So we'll now just get those values from these results, and we'll just draw the bounding box coordinates at the class name above each of the detected object. Next, we need to draw the bounding boxes. So I will just write for prediction inserts for object prediction list. For small mistake. Then we have the class name over here, which will be, then I will just draw bounding boxes around each of the detected object using OpenCV Python. And here we have frame. So here we have the top left corner bounding box coordinates, and here we have the bottom right corner bounding box coordinates. And the color of the bounding box will be green, and the thickness of the bounding box will be 2. Okay. So once we have drawn the bounding boxes, then we will add the class name above each of the bounding box. So we will use cv2.putText to add the class name above each of the bounding box. So here we will just want to put the text above the bounding box. So here I will just pass the uh, top left corner bounding box coordinates, just increasing the height a bit because we want to put the text above the bounding box. And we will define the font over here. The font scale will be 0.6. That would be enough. The color of the text will be green, and the thickness of the text will be 2. After this, drawing the bounding box, we also want to calculate the FPS, like how much frames are being processed in a second. So this is what FPS tells us. frame per second. FPS stand for frame per second, like how many frames are being processed in 1 second. As I'm running it on my liquid CPU machine, so the FPS score will be very low. It's between 0 to 1, like this. By the current time, start time. So we will have to find the start time over here, like this. So now we just want to put the FPS score in our output window as well. So we'll use OpenCV Python put text function. And the coordinates will be 2040. I've just manually defined the coordinates where I want to just put this text. And the font will be simplex. Font scale will be 1. And the thick color will be red of this FPS score. And the thickness will be 2. So if the user want to see the output video, they will write display output video. So if the user want to see the output video, then the view image will be set to true. And if the save image is equal to true, this will save the output video. So, if the view image is equal to true, then I will just show the output video. And the name of the video in output window will be YOLO11 plus SAHI Inference. Here we have the frame, output video frame. And if the user want to save video frame, then write save image. And here we have video writer dot write frame. That looks good. And if you just want to user want to break the loop or close the output window, then we will just, if the user press the 1 key, then the output window will close. We'll just write ECV2 dot wait key 1. So we are adding a 1 millisecond delay between the consecutive frames. Now, once the window breaks or the loop breaks, if the user press the 1 key, then we'll release all the frames. And we'll also release the video writer, which we are using to save the output video, and we'll destroy all the windows. So now what next we can do is, when the user run this script, so now let me just show you. So we need to define the video path. So we just need to have a few things. Okay, so I'm just checking out the code. So now we need to have the input video. We need to define the weights. We need to set the device as well. Okay, like currently it's CPU, but if you have a GPU, then you can set the device as well. Okay, and we just need to define these other parameters as well. like view image or show video, like all this, or save image, like all these parameters. And we can just remove this parameter as well. We don't want to hide the conference score, so we can just remove it. So let's get started with this. So I will just write detector is equal. So I will just call the function. So I will just calling the class over here. Sahi inference is our class. So it's okay. And now I will be just calling this run function over here. This run function. So I will just say detector dot run. So I have the source. In the source, I will just define the input video. So let me add an input video over here. So I will just create another directory, input video. So now you can see we have an input video over here. So I will just write over here, we'll go into the input video, and here we have the input video.mp4. Then we need to define the weights. So here we will just pass the weights path over here. Okay. So now you can see we have the model weights over here. That looks quite good. Yeah. So, but in the weights path, we just need to define. So we want to use the YOLO11 nano model. So I'll just define this. And here I will just define the device as CPU. I don't have a GPU in my local machine. Then we have view image parameter, which will set to true. Then we have the save image, which will be set to true. We want to save the output video as well. So this is view image. Then we have want to set the slice size as well. So it will be 512 cross 512. Like 512 will be the width and 512 will be the height. You can change it as well. So these are the slicing dimensions. And here I will just pass the output video name, which will be output dot. So we are good to go now. Let's run this script and see if there's an error. So we can just fix this up. So I will just write over here Python main.py. So it's downloading the model weights. So now you can see that it's working. And now you can see the processing is very slow. So now you can see that we are able to detect the cars, and like the detection results look quite good. Now you can see that we have combined YOLO11 and SAHI. So SAHI is a computer vision tool that improves object detection, especially for small and tiny objects. And how does SAHI work is that it divides the image into smaller overlapping patches, and then it runs object detection model on each batch. So now you can see that we are able to detect the objects that are very far away, like distant objects, like cars that are very far away. Like you can see over here, these cars are very far away and the results look quite good. So the processing is very slow because like you can see that only like uh, in 2 seconds, one frame is processed. Like we have a FPS score of 0.51. So it means like it took like 2 seconds to process one single frame. Okay. So like we are just that's really slow. The processing on this input video is very slow because it's taking around 2 seconds to process a single frame. So that is the results. So currently, if you have a good GPU machine, the processing will be good. And now you can see that the by combining Sahi with YOLO11, we are able to detect the cars that are very far away. Like you can see that we are able to detect these cars that are very, very far away. Okay. And detection results look very, very promising. Like uh, by combining Sahi with YOLO11, we are able to detect the tiny objects. Like Sahi basically divide the image into smaller overlapping patches and then it run detection on each patch. And you can see that we have set the dimension size as 512 cross slicing dimension size as 512 cross 512. Like yeah, the image will be split into patches of size 512 cross 512, 512 with the width and the 512 with the height. You can make this my size more smaller as well, but the processing will further decrease. Like it, this FPS score will further go down. But if you increase the patch size, like from 512 to 1024 cross 1024, like this FPS score will definitely improve. So you need to have a balance between need to set up a balance because if you decrease the slicing dimension or the patch size very low, this will increase the processing time and uh, the processing on the input this will increase the processing time and the processing on the input video will get slow. But if you set the patch size like increase the dimension size to 1024 cross 1024, this will like faster up the processing. But if you make the slicing dimension or patch size like 256 cross 256, this will further decrease the processing. But if you increase the slicing dimension size, this will increase the processing. So now let me just show you the output video, complete output video now. So let me just show you the complete video. So I have already uh, run this. So I have already processed this on a complete video. So let me just show you how it works. So now you can see over here, like you can see, we are able to detect the very tiny objects as well. And now this is a complete output video, and you can see the results look very promising. Like you can see, we are able to detect the small cars, and they look very, very promising. So now I have also done a comparison with the only the YOLO11 model. Like I've done the comparison between YOLO11 and YOLO11 plus Sahi. So let me just show you this output video as well. So now you can see over here, the results look quite good. Like with YOLO11 and Sahi, the detection has improved. Now you can see that we are able to detect the tiny objects as well. But with YOLO11, we are not able to detect the objects very accurately. Like you can see that some detections are missing if you are only using YOLO11. But with YOLO11 and Sahi, like those detections are also been done. Like you can see that there are some of the cars that are very far away that YOLO11 is unable to detect. But with YOLO11 and Sahi, we are able to detect the cars that are very far away as well. Okay, so now you can see in this video, like we can see that we have done a comparison between your YOLO11 and YOLO11 plus Sahi. And we can see that with YOLO11 plus Sahi, we are able to detect the tiny objects more accurately. And like you can see that in case of YOLO11, some objects are not being accurately detected, but with YOLO11 plus Sahi, we are able to detect those objects as well. So that's all from the studio. Thank you for watching.